Hello friends, my name is Akshans and welcome to CADDD Academy. In this lecture of control system, we are going to discuss the gain margin and the phase margin. So first of all, I am drawing a system response. For that system, the magnitude response is like this and the phase response is like this one. So wherever the magnitude of the response reaches at 1, that frequency is called omega GC, which is gain crossover frequency. Okay, and wherever the phase response of the system crosses minus 180 degree, that frequency is called omega PC, which means phase crossover frequency. Okay, this is the magnitude plot and this one is the phase plot. Okay, so in this magnitude and the phase response, so we can observe that omega GC is less than omega PC. Omega GC is less than omega PC. This is the condition for stability. So wherever the gain crossover frequency is less than the phase crossover frequency, that system is called a stable system. When omega PC and omega GC both are equal, that system is called marginally stable system. Okay, and where gain crossover frequency is greater than phase crossover frequency, that system is called unstable system. Okay, now this is omega, this is magnitude, and this is for phase. This is the magnitude response, this is the phase response. This is 180 degree here and 1 is somewhere here. So this is the omega GC, which is the gain crossover frequency, and this is the phase crossover frequency. So here you can observe that omega GC is greater than omega PC. So this system is what? Unstable system. And for marginally stable system, both omega GC and omega PC are equal. So now moving to the main point, that is gain margin. So the gain margin is change in open loop gain to make the closed loop system unstable. Moving to the formula of the gain margin. So gain margin is equal to the reciprocal of magnitude of the system response at phase crossover frequency. Okay, so this is what reciprocal of the magnitude of the system's response at the phase crossover frequency. We will do the questions on this gain margin and the phase margin to understand these formulas in a better way. Now, if you want to calculate the gain margin in dB, then for that we have to multiply this with 20 log and have to get this linear values log this thing. So this will be equal to minus 20 log of magnitude of system response at phase crossover frequency. Okay, so these two are the things in dB, and this is linear. Okay, and the next one is phase margin. So the formula for phase margin is 180 plus angle or the phase of the system response at omega gc, which is gain crossover frequency, and obviously this is in degrees. Okay, now this is the question. We have to calculate the gain margin of the system whose the response is this one. So moving to the solution, so we know that gain margin is equal to 1 divided by the magnitude of system response at phase crossover frequency. To get this denominator term, we have to know the value of omega pc. So omega pc is what? Omega pc is what? Phase crossover frequency, which means wherever the phase of the system response is equal to minus 180 degree, that frequency is called phase crossover frequency. So for that we have to get the phase of the system, that is, so in the numerator we have what? Root 2, which is a real value and lies somewhere here. So this thing, any value which is lying on this axis is at 0 degree. So for numerator we have 0 degree, and for denominator this is s. S means j omega, and which is lying on j omega axis or the imaginary axis. So s is lying somewhere on this axis and which is at 90 degree. So as this is in denominator, we will write minus 90 degree instead of 90 degree. The next one is s plus 1, which means j omega plus 1. So for this we will write tan inverse imaginary term, which is omega, and the real term, which is 1. So tan inverse omega divided by 1. But again this is in denominator, so we will write what? Minus tan inverse omega by 1. Okay, and is equal to minus 180 degree. So from here we can calculate the value of omega. That will be minus tan inverse omega is equal to minus 90 degree. Okay, so omega is equal to what? Tan 90, and that is infinity. Okay, so now from here we know that omega pc is equal to infinity. Now we have to get the magnitude of the system response at omega pc. So we will write the magnitude of the response, that is root 2 divided by magnitude of j omega is what? Just omega. and magnitude of j omega plus 1 is what? Under root of omega square plus 1 square. So this is the magnitude, and we have to get the magnitude at omega pc, that is infinity. So under root 2 omega is infinity, and infinity is square plus 1. So this whole term is gonna be infinity, and the magnitude at omega pc will be equal to 0. So anything divided by infinity is equal to 0. Now we have gotten the value of this denominator term. We'll get the gain margin, that is 1 divided by this denominator term, which is equal to 0. So the gain margin of this system is infinity. Now moving to the another question, that is phase margin of a system having the loop transfer function as 2 root 3 s into s plus 1. Okay, so for this system we have to get the phase margin, and we know the phase margin is equal to 180 degree plus angle of the response at omega gc, which is gain crossover frequency. Okay, so for this first we have to get the value of omega gc, and for omega gc is what? Where the magnitude of the system response is equal to 1. So magnitude of this thing is what? 2 under root 3. Magnitude of j omega is just omega. Magnitude of j omega plus 1 is omega square plus 1 by Pythagoras theorem, and this is equal to 1. So we have to get the value of omega from here, and that will be our omega gc. So 2 root 3 omega into under root of omega plus 1. Now we will square both sides, so this will be this thing, and our quadratic equation will be like this one. Now we will put omega square is equal to x, then the equation will be the quadratic equation like this. Okay, now we will get the roots of this equation, and that will be minus 4 and 3. You can calculate by using the formula minus b plus minus b square minus 4ac divided by 2a, or simply by using factorization method you will get the roots as this one. So these are the values of x, and x is what? Omega square. So omega square is equal to minus 4 or 3. So from 4 we will get what? Omega is equal to j2, and from 3 we will get the omega is equal to root. From 3 we will get the omega is equal to root 3. So imaginary roots are invalid, and this one is the valid one. Okay, so now we have got the value of omega gc, that is equal to root 3. Now we will put this omega gc value in the phase of the system. So now we will write the phase of the system. So this is of 0 degree, so no need to write this. This is at minus 90 degree, which is j omega. So j omega is lying on the imaginary axis, which is at 90 degree, and as this is in the denominator we will write minus 90 degree. This is j omega plus 1 For this, tan inverse omega by 1, but this whole thing again is in denominator, so we will write minus in front of it like this. Now this is what the angle of the system response. Now we want this at omega gc, and we will add 180 degree to it to get the phase margin. Okay, now minus 90 degree plus 180 degree minus tan inverse of root 3. So minus 90 degree plus 180 degree minus 60 degree is equal to what? Is equal to what? 30 degree, which is the phase margin of the system. Please share the video and please hit the subscribe button.